Welcome, students. We are going to discuss Laplace transform and how to use it to solve initial value problems. Okay. So now Laplace transform, as we said last time, but we'll see in this lecture in details on how it transforms a differential equation into an algebraic equation, and we solve that algebraic equation and push it back to the solution. Okay. So first of all, let's develop some machinery for tackling such problems. So we'll start with finding the Laplace transform of a derivative, right? Because differential equations is essentially you have equations where there are derivatives, right? So let's start with the following. So let f be a continuous function whose derivative is also continuous. Is also continuous. And where are these functions? They say on 0 to infinity. Yep. Then what is Laplace transform of the derivative of f of t? By definition, that is 0 to infinity e to the power minus st f prime t dt. Now we'll integrate by parts. So this here you can take integration by parts. So take u to be e to the power minus st. Your dv is going to be f prime t dt. So therefore your du is minus e to the power minus s e to the power minus st dt, and your v is f of t. So this integral turns out to be e to the power minus st. So v is f of t, minus v du, which is v is f of t, du is minus s e to the power minus st dt. Yeah, uv minus v du is the formula for integration by parts, right? We have u dv is uv minus v du. All right, and u is chosen in the order, certain order. All right, so now we want to basically this limit from here to here will be 0 to infinity, and this is going to be 0 to infinity. All right, so now whenever I'm dealing with limit as infinity, I have to use the limit. So limit as, say, a goes to infinity, e to the power minus st f of t 0 to a, minus of minus, so this will become plus, and s will come out because s, this integral is with respect to t. So s is a constant with respect to t, so it can come out. We have e to the power minus st f of t dt. I'm just rearranging it in a way so that you can read what it is, right? It looks like a, so this guy is, this part here is essentially s times Laplace transform of f of t. Now what about this one here? So if you write it limit as a goes to infinity, e to the power minus s a f of a minus f of 0. Now note that your f of a is has to be piecewise continuous function. So for this to exist, now here onwards we need that if this limit to exist, and this limit exists if your f is what? f is a piecewise continuous function on this interval. What does it mean by piecewise continuous? Piecewise continuous means that it is continuous on every piece and that the function is bounded, is sub-exponential. That means f of t is less than or equal to k times e to the power at for some k greater than 0 and some real number a. Yeah. So suppose that happens, that means what? So if on top of this, if we have that f of t is less than or equal to k times e to the power at for some fixed k and a, right? They are not changing with respect to t. They are not changing with t. They are fixed for some fixed k and a. If this happens, then I can basically replace this limit. So I want to work this limit separately here. So limit as a goes to infinity, e to the power s of f of a is, so since this is positive, this is greater than 0, this is going to be, why don't we compute the limit of the absolute value and show that it's 0? If this is true, so this is an extra condition, all right, on top of this. So we have this is less than or equal to e to the power sa limit as a goes to infinity. And what is f of a? So f of a is k times e to the power at. So this is what is going to happen. And we get this is equal to limit as a goes to infinity. We have k is positive, so we just consolidate the powers now. We get t, so this is going to be a times, so this is going to be a times capital A. So we can take capital A out. We are left with what? Left with a minus s. And this limit is 0 if a minus s is less than 0. That means a is less than s. Otherwise, it diverges. If a is greater than s, then it diverges, right? And diverges if a is greater than s. So therefore, we can write this as following. So this limit is 0. So we get that when this happens, the limit here on the top, this limit will become 0, right? And what do we get in that case? In that case, we'll get this limit is 0, or in that case, we get Laplace transform of f prime t. S is going to be f of L of f of t fs minus f of 0. So this is what happens. You get your Laplace transform basically takes your derivative and maps it onto this guy. So if you look at this, this also encodes your initial value in some sense, right? So let's move on and discuss this further. So we have the following formalization of the this discussion as follows. So if f is a continuous function and f prime is piecewise continuous on any interval 0 to 0 between 0 and a, for all a greater than 0, and suppose that we have this, that f of t is less than or equal to k e to the power t, we introduced this kind of function in the last class. They are called sub-exponential functions for some k greater than 0 in real number. Then this Laplace transform exists. It only exists for all s greater than a, and it satisfies the following, which is what is here. Now, we got about derivative. What about the second derivative, third derivative, and so on and so forth? So let's see. So Laplace transform of second derivative. Now you can think about this as Laplace transform of derivative of derivative of s. Yeah, because we already know for the derivative here how it should be. This is going to be, so this first part is going to be s of L of f prime of t evaluated at s minus f prime of 0, right? That instead of f here in this equation, in this formulation, instead of f we have f prime. Now let's apply the Laplace transform again in this case here. So this is how it should be written. So this is going to be s times in bracket. Now L of f prime of s is going to be, now we use this again. So we have L of f of t evaluated at s minus f of 0, bracket close. This is a simplification of this part is here, and we get, and minus f prime of 0 is outside. So you get, when you simplify this, you get s square L of f of t s minus s of f0 minus f prime of 0. Yeah, so this is the Laplace transform of the second derivative. Now if you try, so try the third derivative. Yeah, try prime of this to see the pattern. And you'll observe the following pattern, that Laplace transform of the nth derivative is Sn of L of f of t evaluated at s. So this minus Sn minus 1 of f of 0 dot 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 all the way until this. Yeah, so this has to be s here and there has to be an s here. Okay, so this is the Laplace transform of the derivative. Now let's see how does it helps us to solve an initial value problem. So again, what kind of problems can we solve with this? We are looking for linear second order because of the second order derivative and constant coefficients, right? And you must be given the initial value problem, otherwise it becomes difficult to solve. So now take Laplace transform on both sides. So we get Laplace transform of y double prime. Now we have to choose what variable we are choosing, s minus Laplace transform of y prime, variable s minus Laplace transform of 2y equals to Laplace transform of 0. Now, why is this true? The linearity of Laplace transform tells you that you can break it. Laplace transform of this is going to be Laplace transform of this, right? And the linearity comes from the linearity of the integral. After all, Laplace transform is an integral, right? You take, so now here we have, and this should also have s in it, all right? So because you're getting an equation in s, now what is Laplace transform of 0 of s? This is going to be integral 0 to infinity e to the power minus st 0 dt, which is 0. So here we get, this implies, so first of all, this part is 0. What about the other part? So here we get let, for sake of brevity, call let y of s. This is just for the brevity of notation. Y. So let's call this as Laplace transform. So now what we'll get in this case, so this part becomes s. So what is the Laplace transform derivative? So if we go back here, we have s squared. So Laplace transform of derivative is s squared f of t s minus s of f0 minus f prime of 0. So this is going to be s squared y of s minus s of y0 minus y prime 0. So this is the first part. So this is what happens to the first part. First part. So let me write like that. Minus, what is Laplace transform of derivative? It is, if you look at this, we have already derived that it is s times, it will be s times ys minus y of 0, right? Using this. So we get here s times y of s minus y of 0. And now you have 2 comes out, then it is Laplace transform of y, which is basically 2y of s. And that is equal to 0. So now we want to simplify this a bit. So we get, this implies s squared y of s, which we need to find out. S of what is y0? Y0 is 1. So s times 1. What is y prime 0? That is 0. Minus s of ys plus y0, which is what? Y0 is 1. Then we have minus 2ys equals to 0. So this implies, take y of s common, we have y of s, then we have s squared minus s, because this is s multiplied by 1, right? Multiplied by 1. So minus s, sorry, the s will come on the other side. So we get s on the other side. Whatever has ys will be on one side. So minus s and then minus 2. And on the other side, this goes on the other side. So we get s, and this goes on the other side to become minus 1. So therefore, y of s is s minus 1 upon s squared minus s minus 2. So this is a Laplace transform of this is the Laplace transform of our solution. So we'll apply. So question is, so this is Laplace transform of solution. So we are asking what function has y of s as Laplace transform? So for that, what we need to do is we are given the table and we need to look from it. Okay, so we are given this table. So we can look into it, or these ones we already know. So the easy ones we have already derived. So you can write y of s as a upon s minus 1 plus b upon s minus 2, b upon s plus 1, right? You're using partial fractions. So the idea is to find Laplace transform of this. Instead of finding Laplace transform of this directly, we'll break it into smaller parts for which the Laplace transforms is well defined. So let's first find A and B. So if you notice by inspection or otherwise, you will see that A is 1 by 3 and B is 2 by 3. Yeah. Or otherwise, you can apply the partial fraction. So you have A times S plus 1 plus B times S minus 2, and then B times S minus 2. Then you need to find A and B. Take S equals to 2. If you take S equals to 2, gives me A times 3 equals to 1. So therefore, A equals to 1 over 3. And then when you put it back, you get B equals to 2 by 3. So you have to use the techniques of partial fraction to do this. So now we get Y of S is equal to 1/3 of S minus 1 plus 2 by 3 times S minus 2, my bad, plus S plus 1. So now then Y of S is basically, so you want to identify now Y of S is Laplace because of the linearity. You have this is some Laplace transform of some function. So what is that function? Yeah. So you need to find out. So notice the following. So if you inspect here, the Laplace transform of, so we are looking for Laplace, what function gives me Laplace transform of S minus 2, right? So I can get from here, if you notice, the exponential function, e to the power what? If t is 1, then you get what? If t is 1, you're looking at e to the power at, right? E to the power at, n is 1 here. Sorry, n is 0. So you get 0 factorial divided by s minus 2 to the power 1. So we get e to the power 2t is 1 upon s minus 2. So Laplace transform of e to the power 2t evaluated at s is going to be 1 over s. So I can replace this now by, so this can be replaced by 1/3 of, this is Laplace transform of e to the power 2t evaluated at s plus 2 by 3 times Laplace transform. So this is, so following the same argument, Laplace transform, this is same as Laplace transform of e to the power minus t of s. Now just take everything in by linearity. So this is going to be Laplace of 1/3 e to the power 2t plus 2/3 e to the power minus t of s. So this is your y of s. So what is the Laplace inverse of this? So Laplace inverse of your ys will give me the solution y of t, which is going to be one-third e to the power 2t plus 2 by 3 e to the power minus t. So this is your solution. All right. So now let's try to think how would we have a general procedure of this form. So general procedure is the following. Suppose you're given a second order constant coefficient linear differential equation, and you're given y of 0 is y naught and y prime 0 is y prime naught. So note that Laplace transform is applied to initial value problems. Now you take a Laplace transform on both sides, then you apply the algebraic conditions, apply the initial conditions. solve algebraically y of s, as we did here. We solved algebraically for y of s in this equation, right? We basically got y of s as we solved algebraically for y of s here, and then we do is the following. And then you basically find out a function y of t whose Laplace transform is equal to y of s. Now note that the main difficulty occurs in the last step, because you have y of t is L inverse of y of s, and L inverse is the inverse Laplace transform. The idea is L inverse of L of yt is yt, and L inverse of y of s is ys. So in practice, you split L inverse y of s into ys for simple function. And what you do is when you apply Laplace inverse here, it is same as Laplace inverse of each one of these. Yeah. So you have Laplace inverse of this y of s is yjt for all y1, y2, yn. Okay. So these are some transform of the Laplace, right? So for example, Laplace of 1 as a function is 1 over s, and Laplace inverse. So this is Laplace of 1 evaluated as, and this is Laplace inverse of 1 over s. So this is how the arrow goes. Similarly, e to the power t, the Laplace is 1 upon s minus a, and Laplace inverse is of 1 upon s minus a is e to the power t. If you have t to the power n, the Laplace is n factorial upon s to the power n plus 1. If you have t to the power p, it is same as, so generalization of n factorial, which is the gamma function. All right, so it is gamma of p plus 1 divided by s of p plus 1. Sine of at is a upon s square plus a. Cos of at is s upon s square plus a. So this is a Laplace transform. So say if I want to say Laplace of cos of at, and the variable I want to use is s, then you get that. And when you apply Laplace inverse of a upon s square plus a square evaluated at t, then you get back to this function. So you see, you go this way and then you go the other way around. Similarly, we'll have Laplace transforms of the other ones. We'll see them as they come along. So let's solve this initial value problem now. So we have find a solution to the IVP y double prime minus 3y prime plus 2y equals to e to the power t. So step 1, take Laplace transform on both sides. So step 1, take Laplace transform on both sides. What do we get? We get s square y of s. What is my y of s? Again, we are going to use this notation for once and for all. So it will be clear that y of s, capital Y of s, is a Laplace transform of yt, right? After all, when you're solving this, you're looking for y of t, right? That's the solution. Minus s of y of 0 minus y double prime of 0 minus 3 y prime, so 3 s of y of s minus y of 0 plus 2 y of s equals to Laplace transform of e to the power t. What did it as? So now we simplify. So this will become s square y of s. What is y0? Y0 is 1, so minus s. This will become, this was only one derivative. So y prime, which is 0, minus 3 sy of s minus y of 0, which is 1. So 3 times 1 is going to be minus 3 times 1 is going to be plus 3 plus 2 y of s Now we need Laplace transform of e to the power t. So if you look at the table, it is, if you look at the table on the top, it is e 1 upon s minus 1. Yeah. So Laplace transform of e to the power t is 1 upon s minus a. So e to the power t is going to be 1 upon s minus 1. Now you take out y of s common. So you have, so let's see, y of s is here, here, and here. So I take s squared minus 3s plus 2 times y of s equals to 1 upon s minus 1. But we have s and 3, which will go on the other side to become plus s minus 3, which is same as if you multiply and add, you get s squared minus 4s plus 1 divided by s minus 1. So therefore, when you find y of s, this is s squared minus 4s, so this is 4. S squared minus 4s plus 4 divided by s squared minus 3s plus 2. Let's simplify this. So this is going to be s minus 2 squared divided by, so we already have s minus 1 in the bottom here. Let's not forget that guy, s minus 1. So we have s minus 1 coming from there. Now when you factorize this, you will get another s minus 1, and then you get s minus 2. So this is going to be s minus 2 divided by s minus 1 the whole square. So now we have y of s, therefore y of s equals to s minus 2 upon s minus 1 square. We need to find L inverse of y of s. Yeah. So how do we do this? So, well, one way is, if we simplify this, so we need to find L inverse of this guy. So let's go and match few things. So is there something of this form? We have s minus 1. So here we have s minus a divided by s minus a square. You do not have the same thing on top and bottom, right? So that won't work, right? One way it will work is perhaps if you could break it in this format. So let's see, is that possible? So we have, I can break it as, therefore y of s is, so I can make it as s minus 1 divided by s minus 1 square divided by s minus 1 square. So this is going to be 1 upon s minus 1 minus 1 upon s minus 1 square. So we know what is the Laplace transform of this, Laplace inverse of this, right? That is going to be e to the power t. So we get that. And what about the second one? For second one, notice the following. We have, so we need s minus something square. So t to the power n, the Laplace transform is, look at this guy here. Yeah. So s minus a to the power n plus 1. So you see that that will work here because we have s minus 1 square. So y of t, I can write by linearity, this is going to be L inverse of 1 upon minus 1 evaluated at t minus Laplace inverse of 1 upon s minus 1 square evaluated at t. Yeah, Laplace inverse. So Laplace, this is going to be e to the power at, sorry, e to the power 1t or e to the power t. And what about this guy? This is, since we know that Laplace inverse of e to the power n, e to the power at is going to be n factorial upon s minus a to the power n plus 1. And this is only true for n belonging to z, right? If n is not a natural number that, or not an integer, then we have the gamma function. But we'll come to an example on that. So if you compare this with, if you compare this with this part here, then you will see that this is going to be t to the power 1, right? Because 2 plus 1, 2 is 1 plus 1. So t to the power 1, e to the power t. So this is what the solution is for your problem. Okay. So again, let me basically walk through this again. You have an initial value problem with constant coefficients. You apply Laplace transform throughout, you get an algebraic equation in y of s, and then you want to basically convert this after solving this as an algebraic equation, you want to convert it in a form where you can read the Laplace inverse from this table, right? So this table will be provided to you in your assessments. Thank you very much for your attention.